Hello everyone. Today we are going to talk about the hydraulic jumps and some of its properties. So the today we will discuss about two things. First is the classification of hydraulic jump, which we have already started, and secondly we will see the formula for energy dissipation in hydraulic jump. So in the last class we saw how we can classify the hydraulic jumps based on the tail water depth. All right. So the first classification was free jump. Free jump will occur when the tail water depth is equal to the sequent depth. So if you see this scenario A, suppose you see this scenario A, what is happening? Flow is taking place through a sluice gate. This is a sluice gate. Okay. So supercritical flow is taking place below this. So the critical depth must be somewhere like this. This must be the suppose the critical depth line. Okay. Now here the conditions in the channel are such that the water which is present in the channel in the downstream, which is called as the tail water depth. Now this depth, available water depth, is called as the tail water depth, that is exactly equal to the sequent depth. So for this particular y1, if you draw the specific energy curve, so for this y1 you will have some sequent depth y2. Okay, for this particular y1 you will have a sequent depth y2. Okay, what is the sequent depth? The sequent depth is the depth for which the specific forces are same. So there will be only one depth corresponding to y1, such that both y1 and y2 have same specific force, that is the sequent depth. And we know that these depths are the depth of hydraulic jump. Okay, so free jump will take place when your tail water depth is equal to this sequent depth. Okay, is equal to y2. So in the channel, water depth is equal to y2. In that case, directly you are going to get a hydraulic jump. Okay, so this is a free jump. But if you see scenario B, what is happening? The tail water depth can either be less than the sequent depth also, and greater than the sequent depth also. So suppose it is less, the available water depth, suppose this is the available water depth, it is suppose less than the sequent depth. Sequent depth is here y2. Okay, we saw last time that what happens as the available depth in the downstream is less, what happens, the initial depth increases slowly up to a certain depth, such that this new y1 dash, this new y1 dash and this new y2 becomes sequent depth. So if on this curve, if you see, then the y1 will keep on increasing till your till its sequent depth is exactly equal to the tail water depth. Okay, so this we saw last time. So in this case, we are getting a repel jump. Okay, we are getting a repel jump because jump is repelled up to this much distance. Okay, so this is the second type, and third type what we saw was a submerged jump, which occurs when your available water depth in the channel basically is more than the sequent depth. Then hydraulic jump takes place initially, but then it is drowned by the tail water. Okay, so in this case we are getting a submerged jump. Okay, in submerged jump the energy dissipation is very low, the delta E, loss of energy, is very low. Okay, since there is no aeration also, air entrainment is less, so we are going to get very low energy dissipation. Now there is one more classification as far as the hydraulic jumps are concerned, that is the classification based on the Froude number of the incoming flow. Okay, so FR1, Froude number 1. FR1 is the Froude number at the upstream. So if this is upstream, and this is downstream. This is y1, suppose this is y2. So Froude number, if you calculate for at this location, this is your FR1. Okay. So based on that Froude number, we have some classification of hydraulic jump. It is given basically by the United States Bureau of Reclamation, USBR. It says that if your Froude number, initial Froude number is between 1 to 1.7, then you have a undular jump. So it can be seen here. This is the undular jump. Okay. Undular jump is not even a jump basically. This just the surface is ruffled, you can say, because see the Froude number is very less now. It is just 1 to 1.7. See, Froude number cannot be less than 1, because if it is less than 1, hydraulic jump itself will not take place. Okay, because the flow should be subcritical. Okay, so it should be greater than 1 Froude number, initial Froude number. Okay. So basically, this undular jump, when it occurs at a very low Froude number, the difference between y1 and y2 is very less. Okay, the difference is very less. Okay, so if you see this, if you see the specific force curve, suppose, okay, so suppose your Froude number is very less. Okay, suppose you are here. So the sequent depths y1 and y2. This is y1 and this is y2. Okay, the difference between sequent depths is not that much. Okay, so undular jump is just a jump in which you can see the surface is slightly ruffled. That's it. So this is the first type of jump classification, that is called as undular. Here the energy dissipation is almost zero. There is no energy dissipated. No energy is dissipated by this jump. Okay, it is not capable of doing that. Air entrainment are also not there. Now, when the initial Froude number increases, suppose now you increase the Froude number from and goes to 1.7 to 2.5. So you are getting a weak jump here, a weak jump. In a weak jump, you can slightly see the rollers forming. So surface rollers start becoming visible for a weak jump. Okay. So surface rollers will be visible. Okay, and you will also get some little amount of energy dissipation. You can get energy dissipation up to 5% to 18% of the initial energy head. This much energy dissipation you can expect in a weak jump. Okay, so if you further go on increasing the Froude number and you increase it from 2.5 to 4.5, okay, then you are going to get something called as a oscillating jump. Okay, so this is a oscillating jump in which you will get some waves which are oscillatory waves on the surface. Okay, so here what happens in the oscillatory jump, the this is a highly unsteady kind of jump, and the surface oscillations keep uh, traveling from upstream to the downstream. So you are not getting an exact location of start and end of the jump. Okay, so this is an oscillating jump. Again, the energy dissipation here is more, and energy dissipation basically can reach up to considerably high, and you can expect about 45% energy dissipation, 45% of the initial energy, dissipation up to 45% of the initial energy you can expect in this oscillatory jump. Then if you further increase the Froude number from 4.5 to 9, if you keep, then you are going to get a steady jump, which is most right type of jump as far as the hydraulic structures are concerned. What we expect basically is a steady jump, because in steady jump, here you can see a steady jump. The toe of the steady jump and uh, the the location of start and end of the jump are very are steady. They do not keep on changing, and you are going to get a clear aeration and good amount of air entrainment, and because of that you are going to get good amount of energy dissipation also. You can expect up to 70% energy dissipation you can expect. Such type of jumps are very good and expected when you are providing energy dissipators. Okay, so they will form exactly in the stilling basin. But if you further increase the uh, Froude number and you take it above 9 suppose, okay, so this type, then you are going to get a strong or choppy jump. Okay, in choppy jumps are not very steady. They are highly turbulent, and you are going to get uh, quasi periodic waves on the surface which may travel downstream. Okay, so this is called as a strong or choppy jump, and here you can expect the energy dissipations greater than 70%. So this is all about the classification of the hydrology based on Proud number. So quickly we'll see a, a hydraulic jump that is taking place in a laboratory channel. So here what we have done, we have created a hydraulic jump using a basically using a OG spillway model. So this is basically a spillway model, and high energy flow is taking place over the spillway, and in the downstream we have created a subcritical flow condition, so you are getting a hydraulic jump like this. Okay, now here we can also see some aeration and bubbles. See, there are a lot of air entrainment is clear, air entrainment is taking place. Okay, and because of that we get this is also called as white waters, and because of that we get some energy dissipation. Okay, now we'll see what is the energy loss in a hydraulic jump. Basically, we know that because of the turbulence that is that occurs in a hydraulic jump, there are a formation of rollers. Okay, these are turbulent structures, basically rollers and all, and we have air entrainment. So because of this, there is a lot of mixing and momentum transport which leads to the dissipation of energy. Okay, along with the viscous dissipation, the turbulent dissipation is also there. That's why we get a lot of energy loss in a hydraulic jump. Now, so suppose E1 is the energy head at level 1 at section incoming flow like this. Okay, so at the downstream if you calculate the E2, then E2 will be way less than E1. Okay, because some energy delta E is lost in the hydraulic jump. So this loss of energy we can write basically delta E will be equal to E1 minus E2, and E1 is what energy at section 1 is Y1 plus V1 square by 2G, and energy at 2 is y2 plus v2 square by 2g. Okay, so you can replace the velocities by a discharge, so you will get this expression, and if you further simplify it you will get an expression which you can readily use in solving problems also. So energy loss in a hydraulic jump is given by y2 minus y1 whole cube divided by 4 y1 y2. So only if we know the sequent depths y1 and y2, only that we need to calculate the energy loss. So we can use this formula to calculate the energy loss. Now the length of hydraulic jump is another aspect. We are not going into the details, but basically it is defined as the length from which the hydraulic jump starts up to a point where the where the flow has tranquilized and so depth is steady. Okay, so it is called as the length of hydraulic jump. Now, length of hydraulic jump is critical issue, and it has to be addressed separately. But basically, if you can remember a simple formula, if you don't have any other tools to calculate it, you can just use this formula 6.9 into y2 minus y1. So you just need to know the y1 and y2. So you can directly get the LG. Okay, that is the length of hydraulic jump. So this is it for today. We are going to continue with the problems from the next class. Thank you.